There has to be a way to do this. What am I talking about? I want to integrate this function, but we see our argument, the cosine of 2x squared, that doesn't have a nice form. You think it's u sub, but then you need a du of 2x in there, and that ain't going to happen. And it's not by parts because that 2x is on the inside of the cosine. So then we need to find another way. But first, let's simplify that guy y, because we know that the cosine is even. So we can go and we can double it and go from 0 to 0.35. Gonna pay dividends later, we'll see, after we integrate that guy, but what? We also graphed it to check that the areas were gonna be the same, and so certainly they will, because that's what we're looking for, the area under the curve. But that integrand is not nice, so we can't just willy-nilly integrate it. We're going to need to approximate it, and we're going to approximate it with the series for the cosine. So we find that the cosine of fish is the sum from none to everything minus 1 to the k, fish to the 2k, over 2k factorial. We got that from Maclaurin series. So we need to make our series for 2x squared. So everywhere we see the fish, we put the 2x squared. We're going to clean it up with a little bit of algebra. And then when we clean it up with that algebra, we need to find the polynomial that's going to represent that guy. So what? Our book said they wanted the error to be no more than... Is that a millionth? No. Tens, hundreds, thousands, 10,000s. 10,000s? They wanted our error to be no more than 10,000. So what? We put that inequality. Whoa, maybe I want the inequality the other way. Anyway, what are we going to do? We're going to go log in. I'm going to use the common log. Because of the properties of common logs, we're trying to get our k out of our exponents. Because the common log's log base 10 of 10 to the minus 4, that's minus 4, sure. Then we use the property where we can put the exponent outside of the logarithm, and then bam, like that. Now we divide both sides by 4 log 0.35. When you guys were finding your k, you did use the log, but not the natural log, right? Yeah, okay. Just making sure you're not pushing my buttons. So we push those buttons, and we find that our k need to be, I know it says smaller, that's why I think I have my inequality the wrong way, because we want to find terms, and the more terms we use, the more accurate our polynomial is going to be. And why was I using 0.35 anyway? I was using that because that's what's being squared in there. And sure, the factorial is going to take care of some more accuracy later, but just to be sure, I just used my basics right there. So then I could have used the entire damn thing, and that would have been fine. We could have found k for that. But I just get in a rough approximation because I'm trying to approximate that guy. So then what? I'm getting choosy, and I'm going to choose k to be 3. So now we see over here on our right side, my series is going to go approximately the first 4 terms from 0 to 3. So then we crank those out because we're trying to find a polynomial that represents that function so that we can integrate it quite nice. And that's going to be that guy. Because I indexed my k, this was 0, this was 1, this was 2, that was 3. Oh, so now I have a 12th degree polynomial. Let me just clean that up, reduce those guys. They calculated, it's on them. So now I'm going to go put that in my integrand because that's my polynomial approximation for the cosine of 2x squared with the desired accuracy. So now it's a polynomial. I wish they all could be polynomials. So we add 1, divide by it, add 1, divide by it, add 1, divide by it. And then we're going to evaluate it from 0 to 0.35, and we see the dividends are paying off now when we evaluate this polynomial up here at the top. Everywhere I see an x, I put a 0.35, and I do that for all my x's. And then it's the upper minus lower. So when we minus the lower, that's a big fat 0. And then we put it into our computational machines, our calculators, and we find our approximation is going to be 0.6958. And then we checked it with the fancy TI, and we're right. And it's all over but the box and flower.